Comparing adjacent rows sequentially is a massive pattern in interviews, like session gaps, sensor readings, and stocks. Using temporal logic efficiently tests if you write scalable queries. Comparing records across different rows in the same table is a fundamental SQL pattern. For rising temperature, we need to find all dates where the temperature is higher than the previous day. While it sounds like a simple relative comparison across our weather table, a naive self-join will trigger a massive Cartesian product explosion. Let's analyze this classic interview question. Here is the trap. Joining the table to itself using only a temperature comparison. Without restricting the dates, the query engine performs a naive cross-join. It matches every row in the first table to every single row in the second table. This generates a 5x5 Cartesian explosion, comparing days that are weeks apart. Why is this a disaster? Because we lack a temporal predicate. The query engine must evaluate all pairs of rows. This results in an O of n squared execution tax, causing performance to crash as our data grows. In production, this naive join turns simple queries into severe system bottlenecks. To resolve this, we write a safe self-join. We bind the join using a strict date offset predicate. This ensures we only compare each day with its immediate predecessor. The query engine uses indexes on the date column to perform direct lookups, executing in O of n log n time and using constant space. A critical edge case is handling missing dates or gaps. A naive key join, like ID-1, fails when dates are skipped. Modern SQL solves this using window functions like lag. By pulling the previous temperature and date in a single linear scan, we handle gaps cleanly and compute senior metrics, like meta-session gaps, with linear O of n space. Lock in this temporal blueprint. Unconstrained self-joins yield O of n squared complexity. To optimize, apply a strict date offset join for O of n log n time and constant space. For complex sequence patterns or session gap analytics, decouple with the lag window function. Master this blueprint, and you will pass your database and SQL design loops. Let's analyze the naive cross-join, the trap approach. Time complexity, O of n squared. Space complexity, O of n squared, generates a 5x5 Cartesian explosion, matching every row against every other row without temporal boundaries. Let's analyze the safe self-join, date offset approach. Time complexity, O of n log n. Space complexity, O1. Applies a strict date offset predicate to restrict matches to sequential days, executing via efficient lookups. Let's analyze the lag window function approach. Time complexity, O of n log n. Space complexity, O of n. Uses linear scan analytical windows to compare contiguous rows in memory, naturally handling date gaps. The interviewer will then ask, how does your query handle non-consecutive dates? For example, if January 2nd is missing. Using datadiff, w1.recordDate, w2.recordDate equals 1 prevents matching across date gaps. With lag, we must explicitly check if the date difference between adjacent records is exactly 1. The interviewer will then ask, how would you apply this to calculate the meta-session gap metric to detect user inactivity gaps? We partition by user ID, order by activity timestamp, and use lag to find the elapsed time between consecutive events. If the difference exceeds 30 minutes, we mark it as a new session.